So today we're going to talk about the second chapter in DSI and focus sort of on inference and sort of impediments to the nature of inference. So one thing to understand when engaging in social science is that the goal of social science is to make an inference. So we should probably at least give a definition of what an inference is. So an inference is a conclusion reached following observation, collected evidence, and reasoning. Um, so this inference is to attempt to explain why things worked out the way they did. So it's attempt to explain causally what led to the outcome in which you're attempting to explain. Now, in the history of political science, this hasn't always been the standard by which we kept ourselves to. During the period really before the 1950s and even still into the 1970s and 80s, political science engaged in what is known as thick description to some extent. This thick description was explaining how things worked, how events took place in overwhelming detail. So that an individual would basically understand the mechanisms of how things move together. But it didn't identify causality. In essence, it is giving a very detailed history explanation, but without really the understanding that ties all those things together, how event one caused or led to event two. And thick description is absolutely important as it provides the basis for us to generate hypotheses and to generate theory because we clearly understand the deep nuances of an event. But thick description in and of itself is simply understanding. And understanding an event, how it took place, is not answering the why it took place question. And so really our goal as social scientists is that inference, is to not just describe how something took place, but to also explain and understand why that event took place. And the why question is really what we're at and really what we're attempting to do as social scientists. That is the ultimate goal of social science, is to explain why events take place, why events in a social context actually continue. There are some impediments to actually drawing those valid inferences. And one of those is culture. So when we attempt to understand culture, it's very important to understand the culture in which you're embedded in order to generate hypotheses, because that culture will inform those hypotheses. However, if we use that culture in terms of testing, it becomes an impediment. So let's think about the context of an in-person class. So let's take ourselves out of this weird situation we're in terms of remoteness and put ourselves back into the classroom. Let's say while I'm giving a lecture, I turn to one of the students and I wink and continue on with my lecture. Now, culturally, that wink in our society can have multiple connotations. It could be I'm attempting to flirt with one of the students. It could be that I'm attempting to share a personalized joke between one of the students that only the two of us get the context of. Or, much more simply, it could be that I simply had a twitch. Now, culture will help us inform what that observation means, but it also can be very, very, very wrong. Because culturally, it could be either of the examples I gave, but there's another explanation that has absolutely nothing to do with culture, and that's simply I had a twitch. And so when we're testing these hypotheses, this cultural understanding can get in the way of actually getting to the truth of the situation. And so while cultural understanding helps us to derive hypotheses, the things we're actually going to test, we need to abstract our tests from the culture in which we're embedded in and studying. So think of this in terms of some sort of cultural explanations we have for the abysmal level of voter turnouts in the United States. And this will come as a shock to no one. Voter turnout in the United States is not great. And while it's been getting better in the past few years, it still hovers at high end. 55% of eligible voters actually turn out to vote. Now, what sort of cultural explanations have we used, especially in explaining youth turnout? Depending on who you ask, it could be youth in this culture are lazy, and the youth of today are especially lazy, and therefore they simply don't turn out to vote as they don't see voting as being important for them. That cultural explanation almost explains itself. But if we look at historical data, we know that the youth in this country have always turned out to vote at exceedingly low levels. That usually a switch hits around somewhere 35 to 40 years old, and individuals turn out to vote more often. So culturally, lazy is a cop-out. And it takes what we generally stereotype the youth of this country with and attempts to use it as an explanation. That's simply not true. So why is youth voter turnout and voter turnout more generally low? And for a number of reasons that have nothing to do with the direct culture of the society, we know that voter turnout is low. There are impediments to registering. There are impediments to actually engaging in the act of voting. And there's a much more serious impediment because of our electoral system. We simply elect too many candidates, and most people don't feel connected with the large number of candidates. And with so many elections, especially like we have here in El Paso, with election after election after election, year in and year out, individuals simply don't feel informed about the candidates and don't feel like they should be voting. So some part of the low turnout may have to do with any sort of these systemic institutional barriers, but it also may have to do simply with the fact that we hold way too many elections. And all of these things can be tested, but our cultural explanations get in the way of actually testing which of these institutional impediments, which one of these things is causal to the fact of low voter turnout. And so when we test what we think of as our inferences, we need to make sure to disengage our cultural understanding of them and attempt to be much more objective and use objective forms of testing when it comes to explaining these phenomena. Another thing that's important to note, especially when attempting to draw inferences, is to know that absolutely nothing is unique in this world. And everything has happened that probably will happen with variations on a theme. And we know this sort of inherently because the way by which we understand our world, the way by which we make sense of it day in and day out, is we examine patterns and we make comparisons based upon those patterns to draw our essence of understanding for the world. And we do this almost unconsciously. When you meet someone and get an initial impression of how they are, you're basing that impression not just off of them, but off of other interactions that you've had, and you attempt to put them and typecast them and stereotype them into a role. We naturally do that. That's our natural response as human beings. Another example is, for those of you in El Paso, and also elsewhere, but this definitely works in El Paso very well, to simply think of the weather. I've been outside today. It's hot. I know what time of the year it is. I know without looking at any meteorologist or any prediction of what the weather is going to be like tomorrow, I'm pretty certain it's going to be hot. And I'm making that inference off of patterns of exposure to an event that repeats itself. So I have a lot of data to predict tomorrow and understand tomorrow, even though we aren't there. The reason why comparisons are important is because it helps us define events. It helps us define occurrences. So let's say, for example, I assume tomorrow is going to be hot and dry. Well, let's happen that tomorrow is cold and rainy. Well, without comparison, I don't even know that that event is rare. Without comparison, I don't know that that event lies outside of the norm. So when we say an event is unique, and by unique we mean one of a kind. It's a cop-out because explaining without reference to other events, even if that reference to other events is to differentiate the occurrence from other occurrence, is absolutely lazy. And it's also not how we think as individuals. If tomorrow is rainy and cold, we will be making reference to it in terms of what we already understand as the norm. And so our comparison is what draws that event out as rare. And this ability to compare and draw inferences, even if we do it from a small number of cases, can absolutely be scientific. It's easier to do with a large number of cases. So with the weather, for example, I've lived in El Paso now for 8 years. I have a pretty good grasp on what tomorrow is going to look like based on lots and lots of data points. But if you moved here last week and you only have 7 data points, your inference can still be scientific based on those data points. And to understand those data points, we have to be able to actually summarize the data that we have. So think again of this difference between someone who moved here last week and someone who's lived here for their entire life. You can summarize that data in the same way so that individual is simply dealing with less data than an individual who's lived here for his lifetime. So when you're summarizing that data, you want to make sure you're focusing on explaining the outcomes that you're seeking to understand or predict. So in this context, we have to be pretty clear about what it is that we're trying to predict and how it is we're going to summarize that data, because how you summarize that data matters, even if it is the same information. And let me provide you with a very relevant example that will be purposeful for this class. When we think of ways to summarize our data, there are a number of ways, but in the terms of this class, you'll become very familiar with the ideas of mean, median, and mode. And those are 3 different ways to measure a variable's central tendency. That's to say what is the most likely point of data. But they're very different ways to summarize that data. And so when we think about summarizing our data, when we think about describing our data, we need to take an idea, to take a real understanding of what our data actually means and think through if we're summarizing our data in the most effective and also accurate way. Turning to the actual data itself, we need to talk about the differences between what are systematic and the differences are non-systematic. And it's important to note that in any data, qualitative or quantitative, both systematic and non-systematic differences will always be present. Most of the time as social sciences, we're interested in those systematic differences because we think that those systematic differences are what explain variations in outcome. And so while we're interested in those systematic differences, if we fail to take into account the non-systematic differences that exist across observations, we might ultimately bias our influence, or bias our inference, I mean. And so focusing on the systematic without an idea about non-systematic differences will absolutely usually take us down the wrong path and make our inference not as accurate. Now, this can be a circumstance of measurement error. We simply did not measure the content, measure the observation that we wanted to, or the concept that we wanted to in a way that accurately predicted or accurately examined the model. It may be a problem in our research design. We may have crafted our observations in such a way that any inference we take is going to be a blend of systematic and non-systematic differences. Or it could simply be random chance. We could have a very accurate device, that is a very accurate measurement device. We could have a very sound research design, but random chance enters in and affects our inferences. Now, when we think of random chance as possibly being an issue, and also measurement error, this is more problematic when you have fewer and fewer cases, which tends to be the circumstance when you're doing qualitative research. Now, in quantitative research, when you have a large number of cases, so we think of that in circumstances of a large n meaning number of cases. If there is some random chance variation in how you're measuring things, at the large n, that random chance isn't as much of a problem. Now, measurement error, if it is systematic, is absolutely a problem. Non-systematic measurement error is also a problem, and they're solved in different ways. But when you have a small n, any sort of error in terms of the accuracy of the systematic differences and non-systematic differences you're attempting to measure can really throw things off. And so we understand that the environments in which we're observing are by their nature probabilistic. That is to say that we generally have a good idea about how things are going to be carried out. And therefore, when we model things or attempt to explain them, that's really what models are, is they're an attempt to explain reality. If you were familiar with you or someone you know who built, for example, model cars or model airplanes, we recognize that those aren't actual cars and airplanes, but they are models. They are a simplification. They are a representation of a much more complex device. Well, when we build models to explain events, they're much more simple than the actual event we're trying to explain. But the event we're trying to explain is probabilistic. So our models have to take into account that probability. And that's why in quantitative research, almost all statistical models that we work with are based upon this idea that probability is built in. And therefore, in qualitative research, you have to build in this concept that what you're observing is also probabilistic. So in the context of quantitative social science, this is an equation that you will come across all the time. And that is y is equal to beta 1 plus beta 2x plus u. So in the context of what this means, it's that y is our outcome variable. B1 is what we call the intercept. And B2 is the effect of some variable on y. The u part, that's error. That's all of that random chance, measurement error, research design failure is built into that u. And so we attempt to predict probabilistically, taking into account that there can exist random error. And so I'm going to show you some examples of those shortly. So what is a regression? So I've already told you that this is an equation for a regression. You should be really familiar with this equation, though you may not have seen it written in this form. You have probably seen this as y equals ax plus b. This equation, as written, is simply how to plot a line. That's all it does. It is the best summary for two pieces of data point, or for two variables, in terms of a line. And u is the error of what's left over. So what does it mean? It means that we summarize some relationship, dependent variable y, with some independent variables x. This is the starting point for all statistical models. And it's also a way to think about qualitative research. You're attempting to explain y given x, and there might be multiple things that help influence y to take place. Let's say y is, let's say, a coup. And so coups don't just happen. In political science, we know that coups are the end of some systematic variables that influence the likelihood of a coup to happen. That's what that x is in that equation. Those are the number of variables. Now, y is the outcome. Does a coup happen or does a coup not happen? Let's say we have all the countries in the world, and we want to explain what predicts the likelihood of a coup to happen or not. Regression is a tool that can help get us there. So what does regression actually look like? Let me give you an example, because I want you to start thinking this way right now. Here's a regression that is attempting to predict a son's height from his father's height. So if we think of the equation, y in this context is, not shockingly, the y-axis, and x is the x-axis. B1 in the previous equation would be the point in this graph where the line crosses the y-axis. Right here, it's around 61-ish. B2 would be the slope of the line. That slope tells us that, on average, if your father, for example, was 60 inches tall, then the son will on average be 64 inches tall. That's what this equation tells us. And so the slope, the effect of x on y, is about 4 inches, give or take. Now, as you can see, there's a large degree of variance across this point. So you can see the x's in circles. Those are exactly on the line. Those are the mean values. Now, you see that there are a lot of x's above and below that mean value. All of those x's are error, because we have to recognize we're dealing with probability. All of those x's are error, and the probability is actually the slope. So that is the most likely effect, would be a 4-inch difference between father and son. But also, as we can see from the data presented on the screen, there's a large degree of variance around that point. So while we can control for other factors and attempt alternative explanations, we need to know that this variance actually exists. Now, this is really nice, clean, neat data. Data doesn't generally exist like this in social science. Let me give you an example of what data looks like in social science, and it's messy. This is, from the data set we'll be using for this class, an attempt to predict how individuals feel about the Democratic presidential candidate based upon their feelings on the Republican presidential candidate. So as you can see, this has a negative effect. So line going down means negative. So as individuals feel more positive about the Republican presidential candidate, they should feel less positive about the Democratic presidential candidate. That should make just complete intuitive sense to you. If you are a huge fan of Joe Biden, there is a low probability, there's a fairly decent probability you're not a huge fan of President Trump, and vice versa. But as you can see, all of these little dots are individual data points. They don't at all really look like they converge on that line. So let's take, for example, the most bottom left data point. There is an individual out there who looks to be 0-0. So they approve not at all of the Republican presidential candidate and not at all of the Democratic presidential candidate. Perhaps you can work into your mind how that makes intuitive sense. Look to the top right. There was an individual who responded that they 100% love the Democratic presidential candidate and also 100% love the Republican presidential candidate. Now, I don't know who that person is, and that person doesn't absolutely make sense to me, but they exist, and they're the error. And every dot that isn't on this line represents an amount of error in our prediction. When you work in qualitative research, it's more difficult to identify the error because you don't have as much data. Let's say we attempted to make this prediction just using this class. So feelings of the Republican president predicting the Democratic president. I think there are 45 of you in this class. That's a fair amount of data. But that data in and of itself is not representative of El Paso, nor is it representative of Texas, and it's certainly not representative of the United States. It's a small N study. It's not exactly qualitative, but it's a small number of cases, which is defining of most qualitative work. How accurate would our predictions be? Well, it really depends on what we're attempting to predict to. If we're attempting to predict to opinions of political science majors and minors at the University of Texas, El Paso, that data might be accurate. Might. Once we extrapolate beyond there, it's difficult to say how accurate it'd be. In fact, I would assume it's going to be not accurate of the population as a whole. When you're working with a small number of cases, you have to work much harder to rule out alternative explanations. And to that end, you have to be much more careful about non-systematic and systematic error in the collection of your data.